right away. As we are all aware, this is a session which will throw light on driving the need for innovative memory solutions. We already have the speaker ready. Ladies and gentlemen, put your hands together for Dr. Ron Black, the President and CEO of Rambus Incorporated. Welcome to you, sir. And in the interest of time, I would hand over the session straight away. Over to you.
Great. Do we have the slides, please? Well, first of all, thank you very much for coming and attending. This is my second opportunity to speak here. My first one was last year. It was a very interesting forum, and by the sheer number of people, I think this year is going to be even better. If you attended my talk last year, you might remember it. It was a little bit about the economics of the semiconductor industry, how those economics are changing. How in the hardware area especially, early stage companies, entrepreneurs are finding it difficult to access capital, and some of the implications, especially in terms of cost arbitrage with low cost design centers, and how just low cost might not be good enough. So in the spirit of this conference and the theme that we have, I want to make it a little narrower presentation. It's about innovative memory solutions. And I think you'll find it interesting, and if you're an entrepreneur at the end, please stay for that one slide, because it's going to be perhaps really important. So I have to say that just a few years ago, I wouldn't have even thought I would have been giving this presentation. I wouldn't thought that I would have been working at Rambus, for the simple fact that the memory business was known for bad economics. It was in general the memory business, but especially the DRAM industry, which is largely what Rambus plays in. And early in my career as a junior executive, I remember this statement from Warren Buffett that I found incredibly impressive and a direction for, I think, all executives. And that is, when management with a reputation for brilliance tackles a business with a reputation for bad economics, it's the reputation of the business that remains intact. And given that memory was such a bad business, it was something that I avoided for a long time. In fact, early in my career, I worked at IBM, and I was part of a strategy group that looked at the memory business in the early 1990s, concluded that it had not earned its cost of capital in approximately 20 years, that it was unlikely to earn its cost of capital going forward, and so we concluded to stop the memory business. Having said that, I cannot tell you how much different I feel about the memory industry, and especially in light of the thought processes here from a fab standpoint, it may be a completely different area for consideration that I doubt even a year ago that you may have done it. If you look at some of the key companies, and I think this is a demonstration of the change in the memory business, companies like Micron, pure play in the DRAM and non-volatile business, their market capitalization has gone up by about a factor of 5. Companies like SK Hynix has gone up a factor of 3. So there is real value created in these companies, and it's something that all entrepreneurs, especially here, should look at. So here's the agenda quickly. I'm going to talk about megatrends driving the technology, a few of the challenges, and there's really two that are incredibly important. The first is power, and the second is scaling, which really relates to cost. Third is the memory opportunities, and the last but not least is some things that you might want to consider here in India that could be particularly relevant. So, like much of the semiconductor industry, there's two fundamental poles today that are driving things on the DRAM side. One is in the mobile, and that's all about power. And in terms of memory, you want a certain minimum frequency for performance, and you want the absolute lowest power. In terms of the server side or cloud computing, you have a similar but inverted problem. There, you want to have the absolute fastest speed and the lowest power at that fast speed. And of course, all of them have to be cost competitive, and they have to have very specific features and functionality that the customers are looking for. So I think these trends are going to drive the industry for a long time. But there is, of course, a completely new megatrend, and that is the Internet of Things. I actually ran a publicly traded French company that did what was called machine-to-machine in the 2000s. That was the precursors to the Internet of Things. And I can tell you it's a very challenging business, not so much because of the innovation, which is challenging, but because it is fragmented and massively different from product to product. It goes from everything from something in your car to wearables like my little Nike Fuel Band, which I thought was a gimmick, and today I wouldn't be without it. It's something that I use almost on a daily basis, and it's very interesting. In terms of design, however, be it memory, processors, security, connectivity, the Internet of Things is definitely going to change it, and change it for the more difficult. We're going to have a lot of challenges on power and a lot of challenges on performance. So let me talk about a couple of these key challenges in the DRAM industry and give you a few industry references so you can see a little bit of detail about the economics and some of the technology. The first is the power problem. So this is a chart that was sourced from IDC, and it goes from 1996 to 2012. I know it's very hard to see. But it talks about the spending in US dollars, billions, of new servers, which is in the red, and that's about $50 billion a year. The server management admin costs, which is an OpEx, not a CapEx, and that's in yellow. And the power and cooling costs. And you can see that there's almost been a linear, the gray, of the physical server base, which is approaching 50 million, and installed base. And as you can see, the spending for CapEx, the red, has been kind of flat. The OpEx from a server management has been increasing, but at a decreasing rate. But the power side of it is small originally, but it's been increasing, and I would say increasing at an even faster rate, especially if you had the data from 13 and projected out into the future. So this is a huge problem. In terms of memory, it contributes significantly for that, and I'll explain why in a little bit later. And here's two sources of information. The first is for Barossa et al. From Google, and that talks about the data center in 2007, so a few years ago. But as you can see by the pie chart, on the right, CPUs take up about a third of the power, the DRAM just under a third, and everything else just over a third. The chart on the right is from IBM in the Flash Memory Summit, more recent data in 2013. It's careful to not talk about the actual dates or the power details, but it shows that the power consumption and breakdown, the power consumption is increasing dramatically, almost exponentially, over the period that they referenced. And the amount that's associated with memory in this purple center is the biggest part. So leave it to say that memory is a key element in the data center and a particularly natty problem from a power perspective. So here's why. In a classical memory system, you have things that are static and have power in them, things that are dynamic and have power but have to be refreshed constantly, and things that can be non-volatile, things like flash memory. And flash has the lowest power consumption, but it's inherently slow. SRAM has the highest power consumption, but it's very, very fast, and DRAM kind of fits in the middle. As you can see, it has, the slide. You have a problem of active and idle power. And because the DRAM is constantly being refreshed, it consumes an enormous amount of power. So you'd say, well, we should just stop using DRAMs, take everything to flash. And there are companies in the industry that are looking at doing that, but the data rates for the flash technology are not sufficient to maintain the performance. So architecturally, at least today, it doesn't completely work, even if lots of entrepreneurs across Silicon Valley are looking at ways to deal with that. So let me move on to the second key problem, which is costs. And this is a problem especially with scaling of the technology. I absolutely love this little drawing on the right-hand side by S.Y. Cha at Hynix. It was from an IEDM short course in 2011, and it shows the structure of a typical DRAM. And you see this long piece on top, that's the capacitor that actually stores the charge that references whether it's a 0 or 1. When I started working, they were very small, and they had shallow trench, and then they had deep trench, and now this is incredibly long. And while I'm not a mechanical engineer, I did a little bit of mechanics in college, and I remember how complicated it is to put together these many materials and have that type of aspect ratio and have it stable. In fact, if you talk to the smart people in the industry, which is certainly not me, but there's a lot of them at Rambus, the scaling of this capacitor is going to be increasingly more difficult. And so what that means as you approach the physical limits of design is you either have to have a new bit cell technology, so something different than what you currently have, or you have to find other ways to take cost out at a system level, or to change the dynamics so the DRAMs can be used when they're maybe not quite as reliable as they used to be. And that's a very big difference also. In the non-volatile space, the controllers that you have, because the endurance of non-volatile memory is not that good, there's a lot of intelligence built in that says, well, you shouldn't use this one too many times, this particular bit is not going to work. But they don't really do that in the DRAM. The DRAM industry is really relying on exceedingly high quality, and as a consequence, when you try to build taller and taller structures with finer and finer pitches, it's going to be incredibly problematic to take the cost down. And here, in fact, is a chart that shows that problem. This is from the DRAM Exchange, IDC, and ASML, and it shows the dollars per gigabyte of DRAM and NAND flash over time. And the little arrows on the right are some liberty from my team, but I have to tell you that they're concerned that there's going to be more of an asymptotic cost reduction to DRAMs, and NAND will continue to go down. Now, NAND going down in price is very good because you'll have lower cost cell phones. There's nothing wrong with that. There's lots of backups and intermediary use. That's also very good. But fundamentally, in the architectures that exist today, to achieve the front of screen performance, whether it's in a server or a PC or your handset, you're going to have DRAM. And if it's not going down in cost, we're not going to have the same benefits that we've been seeing for the past 10 or 20 years.